next section we're talking about scatter diagrams, which is again something you've seen before. We are not really going to make scatter diagrams by hand. We're going to pretty much use the calculator for all of these. So what is a scatter plot for a scatter diagram? Do you remember? It's, you just put your dots for all of your points.
Wait, but it has a beginning and an end.
Yes.
They touch the line.
Yes, it's not like a continuous line. So we're looking at those dots. So you're thinking about like line of best fit, which we will talk about more, not really today, but tomorrow. So basically you've got your independent and dependent variables, or here we usually talk about them as explanatory and response variables, and just plotting those points. So let's take a look. We'll just jump right in with the first example here. So this data is shown, it's a study on drilling rock. The researchers want to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So if the deeper they start, does it take longer to drill your 5 feet? So here we have our x, that's the depth at which we begin. Our y is the time it takes to drill. I want a scatter diagram. So we're going to do this on our calculator. You need to go to your L1 and L2, and you enter your x in your L1 and your y in your L2. Stat, edit, clear out what's there. And enter your x and y. Now if we go to second stat plot, you might have both plots turned on from yesterday, so we only want one plot here. I have my plot 2 on, so I need to turn that one off. And then I'm going to go into my plot 1. I want it on, and the scatter diagram is just the first list there. So the very first option just has the dots. And then if you go to zoom, number 9 is zoom stat, so it just kind of zooms to wherever your points are. And so it gives us our scatter diagram. Did everybody get that? We are going to talk about the relationship. So you guys talked about when you did this back in your algebra classes, you know, positive linear, negative linear, those types of things. So on your notes handout, this does tell you kind of a list of what some of these things might look like. And these first two are very linear responses. This one's nonlinear. What does it look like?
Hello.
Yeah, it's kind of, we'll call it more of like a quadratic. It's like an upside down quadratic there. You know, there's definitely a pattern to it. It's not a linear pattern, but we'll talk about some of that. This one, it doesn't really look like as much of a relationship. So what would you call ours? Does it look like there's a relationship?
Yes.
Yeah, it's not a real strong one, but there is a somewhat of a linear, positive linear relationship. When you've done this before, you've used like weak or strong. If all the points are really close together, you called it a strong relationship. If they're a little more spaced out, it was a weaker one. So this would probably be a weaker relationship, but there is some kind of pattern there. So we need to be able to measure how good of a relationship this is. And we are going to look at what's called a linear correlation coefficient. Right, so that is called R. Do you guys have your formula sheets? Of course, yes. So we are now into the chapter 4 material, and the very first thing on there is the correlation coefficient R. And so this is one of those things, kind of like standard deviation, it's very time consuming to do by hand. I may have you do 1 or 2 by hand just so we kind of learn how, but it would be small data sets. Otherwise, we will use our calculator for finding those. So all of these things in this formula we've seen before. This E looking thing, that means the sum. It means you're adding up a bunch of stuff. In here, x of I is just the value of an x minus the mean of x divided by the standard deviation of x. And then you have to do the same thing for your y's. Divide by n minus 1. We know n is the number of points that we're looking at. So with our correlation coefficient, it should always be between -1 and +1. Okay, if it's really close to the 1 or the -1, that's a strong relationship. Negative being a strong negative relationship, so like a decreasing line, positive would be an increasing relationship. If it's close to 0, that's like saying there's no relationship. It doesn't have units, it's not resistant. What did we say resistant was? It's been a while since we've used that term. Resistant means if you throw an outlier in there, it doesn't change. So when I'm saying it's not resistant, that means one outlier is really going to change this value. So kind of like the mean, the standard deviation, an outlier has a big impact on this value. So this is just kind of showing you, like this first one, that would be a perfect R equals 1. Perfect linear relationship. This is like R equals -1. These, you're still going to have a positive R. It'll be fairly close to 1, so probably like a 0.8, 0.9. This is still positive, but you see the points are getting more spread out, so your R is going to be a smaller positive, so like a 0.4 type thing. These would be negatives. This is looking at your R would be pretty much a 0, very, very close to 0 because there's no relationship. Here there is a pattern, but R is measuring a linear relationship. So is there a linear pattern here? No. So this would be another case where your R is 0. So R is a linear measure, linear correlation coefficient. It's not going to tell us if there's any other type. All right, so let's look at this. Let's do an R by hand, and then we'll talk about doing it on the calculator. Okay. So I want the linear correlation coefficient of the data. Let's kind of make it a little bit easy. Let's get our mean and standard deviation from the calculator so we're not doing everything by hand. So if you go to your calculator, let's enter this in your L1 and L2. So then, if I just want to get all my information at once, you can go to Stat, Calculate. You can either do one variable stats and do it once for L1 and once for L2, or if you go to two variable stats, your first one is L1, your second one is L2. So in this, my x bar, so the mean of the x was 4. Standard deviation for the x, we're going to go with sample, only use the population if I tell you it is the population. So 2.4495. Standard or mean for your y is 10. Standard deviation for the y is 5.612. Thank you. Okay. So what we have to do is for each of these ordered pairs, we have to do the x minus the mean of x divided by standard deviation of x. going to do the same thing for our y's. I guess I should maybe forward appears here to help us. So we'll do the y minus the standard deviation, or the mean of y divided by standard deviation of y. And then we have to multiply those things. So this is even more time consuming than the standard deviation that we've done by hand. But it's good to work one out, just to kind of see what we're doing and understand the calculations a little more. So, I'm going to do this on my calculator. So I'm going to parentheses, my first x value is 1, minus the mean of x is 4, divided by standard deviation of x is 2.4495. Do you guys know that if you just hit second enter, it'll bring back up what you just typed in? And so for the second one, I just need to change my 1 to a 3. This one has the same x value of 3, so this x one is the same. And I have it as my x is a 6. And then a 7. Make sure you try at least one of these on your calculator so you can make sure you are understanding where my numbers are coming from. I just did my x, so for the first one it was 1 minus the mean of x divided by the standard deviation of x. So everybody know where I got those numbers? So now for my y column. So for the first one, I do my y value. So my first y value was 18 minus the mean of my y's was 10 divided by standard deviation for y, 5.6125. So for the next one, all you do is change that 18 to a 13. Everybody understand how I have filled out my table so far?
I'm kind of confused.
Okay. So for like this one, for instance, okay, you take the y value. So the y value here was 13 minus the mean of our y's, which was 10, divided by the standard deviation of y. So y was 6. And so really all you're doing as you go down this table is I'm just changing that y value to be the y value of those order pairs. Other questions? What do I need to do for this? Yeah.
Our first and last numbers that we entered on our x, are those because we have to have them touching the x's?
No, I just did them because that was what was in the table of data I gave you originally. You're talking about this x and this x. I just did the table that was given.
But what did you mean when you said they had to, or the whatever we got had to be in between -1 and 1? Is that
The
the
final R value. So we haven't got that yet. Yes, ma'am.
I got all those points except for the last one.
Did I make a mistake?
also-
Yeah, I typed in 7, I think, instead of 4. Okay, Okay, so you should do 4 minus 10 divided by the 5.6125. Alright, is that better? Okay, thank you. And then what do we have to do for this final column? Multiply. So you're just taking these two things and multiplying together. So the one we got in our x's and the one we got in our y's. And as we've just seen, it's a good idea not to trust me to double check my calculations. So far, so good. Okay, so now look at your formula. We have found all of these products. What does this say we have to do with those?
Divide by n.
Add them all up and divide by n minus 1. So if I add up this column, divide by n minus 1. What's my n?
10.
N is the number of points. We count x, y like that word pair as 1 point.
5.
So we have 5, so divide by 5 minus 1. So we get an R of negative 0.9456. It is important on these that you are keeping decimal places. You know, if you just round everything to 1 decimal place, you are going to have a significantly different R value. So we need to try to keep those 4 decimals as we go through that. Any questions there?
So this would be strong because it's close to -1.
Yes, it is a strong negative relationship. So it's a decreasing line. It's very linear, the negative 0.94, so that's very, very close to -1. So it's a very strong relationship. All right. So can we agree that this isn't all that fun to do by hand? I guess it's a lot of easy points, just a bunch of plugging things in your calculator, but very time consuming and not practical to do that by hand. So let's talk about on our calculator what we would do. So we may have to change them. All right, here's what I need you guys to do. I need you to go to second and the 0 button. It takes us into our catalog. So there is a feature on your calculator which gets turned off sometimes. We need to go all the way down to the D. We need diagnostic on. So we're just going to scroll down, and my computer is very, very slow. so you guys can scroll much faster than I can. Okay, so there's diagnostic off and then diagnostic on. Did everybody see that? You just need to hit enter and it'll say diagnostic on and hit enter again. This is just a feature that gets, anytime you reset the calculator, it automatically turns it off. So if you are not seeing the R when we do some of our calculations, we just need to go back and then turn this on. Okay. Well, you guys don't have Chromebooks this year, so if you're using my calculators or your own personal one, once we turn it on, it should stay on unless we have to reset your memory. So you shouldn't have to do this every time. So now we need to go into our stat calculations. And this is a linear relationship. That's what we're trying to measure. So we are going to go to number 4, a linear regression. And it should just have your x's as L1 and your y's as L2, so we can enter through all of that. And this actually gives us the line of best fit. So you've used this feature before, probably trying to find the line of best fit. We'll talk more about the equation of that line itself tomorrow and the next day. But what I want to get from this is the R value. If you don't have the R and the R squared, that means your diagnostics are off and you just have to turn them back on. So our R, we got negative 0.9456, which is exactly what we got when we did it by hand. So just confirmation that we are correct, but we will pretty much exclusively use our calculator to get this calculation.
So when we use our calculator, do we still have to do like the graph or the whatever?
A lot of times I'll ask you to look at the graph first to make sure it is a linear pattern.
Okay.
Is that okay? Yes, ma'am.
How did you get there? On the calculator.
We have to make sure that a linear relation is appropriate on our problems. So if you see the next slide, it has testing for a linear relationship, what we need to do. There is actually a table that can be used to check for this. So we have to take the absolute value of our correlation coefficient. So we just look at the positive, find the critical value in table 2, and if the absolute value of the correlation coefficient is greater than the critical value, we can say it is linear. Okay, basically what's going to happen is as you throw in more points, that can affect your R value. So we can't just necessarily say, well, it's got to be 0.9 to be linear. We have to have a way of determining that. And so there is a table that we will use to do this. So hopefully, if you look on your formula packet, it's the back of the second piece of paper. There is table 2, your critical values. So what was my N on this problem that we had? My N was 5. So if you look at your 5, your critical value is 0.878. So the absolute value has to be bigger than 0.878 for us to say it is linear. And we had negative 0.9456. And that is bigger than the 0.878. So it is linear. Okay. Does everybody find that table?
Where are these numbers coming from?
The critical value numbers don't how many points we had. So you'll notice as like your number of points goes up, your critical value gets smaller and smaller. So it has to be a weaker relationship for us to still say linear as we have more points.
So we got 8.878 from the number?
Yeah, if we have 5 points, the critical value is 0.878. So we have to be bigger than that to say it's linear.
Okay.
All right. So, let's see, next thing I have on here, see if we can get through one more example. Can you talk about a lurking variable real quick? So, lurking variables is something that can be related to both your explanatory and response that might cause it to look like there's a linear relationship when there actually isn't. For example, if you look at ice cream sales and crime rates, there is a strong correlation between those. So does that mean that selling more ice cream makes the crime rate go up? That doesn't really seem reasonable. So even if we just looked at those, there would be a linear relationship, but it's not actually the cause. What could be a lurking variable? Location. What would be something else that would cause ice cream sales to go up and crime rates? Heat. Do you guys eat more ice cream when it's hot outside? Do crime rates typically go up when it's hot outside? Yes. So just because there's a linear relationship doesn't mean you can say one thing is causing the other. All we can say is they're related, but we can't say there's the cause, that selling more ice cream means there's going to be more crime. Okay? So that's something we'll talk about a lot. Just because there's a relationship doesn't mean one caused the other. All right, we are almost out of time, so we're going to kind of breeze through this one. I just showed a table. This tells you the number of sodas drank per week and bone density. And I went ahead and gave you, this is what the table, or the scatter plot looks like. So, the correlation coefficient on this was a negative 0.806. Okay, we had 15 women in this study. So look at your table. When your n is 15, what's your critical value? So is the absolute value of this greater than the 0.514?
Yes.
Yes, so that means there is a linear relationship. Okay, does that mean that drinking soda decreases your bone density?
Not necessarily.
Not necessarily. It could. We found a relationship, but it doesn't mean one causes the other. So all you can say is there's a linear relationship, not that there is a cause. Okay? Just have to be careful on our wording there. All right.